Okay, before I revise with you the circle geometry angles, circle geometry theorems about angles, I'm just going to remind you, don't forget year 7 stuff. If you've got parallel lines and there's a transversal, you know that the alternate angles are equal, you know that the corresponding angles are equal, and you know that the co-interior angles are supplementary. In other words, they add up to 180. Don't forget that isosceles triangles are the absolute business. They come up in circle geometry all the time because whenever you draw two radiuses, you've got an isosceles triangle if you connect the 2 points on the circumference. So everything you need to know about this triangle is given to you by me saying that's 50. If that's 50, that's 50. And if they're 50, then that's got to be 80 because there's only 180 degrees to go around in a triangle. So don't forget, always year 7 geometry is still available to you. Don't forget to look out for isosceles triangles. You don't need any circle theorems to find isosceles triangles. But what are those circle theorems? Well, a year 7 would be stuck unless I told him that that was parallel to that. A year 11 student who knows circle geometry does not need to be told that that's parallel to that because they know that that's equal to that and that's equal to that. Okay, the proper name for that, people call it the butterfly. The official name for this is called angles in the same segment. Knowing the official names for the theorems is very important. First of all, it gets you 1 mark. Second of all, it saves you time because instead of having to scratch around for what you consider to be a cogent history, English or geography type explanation, you just state the official thing and everyone will understand what you mean. Okay, so that's one of them. There's another one that has an informal name which I don't like because the informal name, which is the rocket theorem, only refers to one of the 4 possible pictures. What the 4 possible pictures have in common is that you start with 2 points on the circumference. I call these the 2 anchor points. And in all 4 of the diagrams, you scoot to the center. Center is always marked with an O. And in all 4 of the diagrams, you also scoot to the circumference. If you scoot right to the other side, you get the traditional rocket look. If you scoot way off to the side, you get what looks like a butterfly, but which in fact is not. A butterfly had all 4 points on the circumference. This doesn't. This has 1 at the center. That's the point. All 4 of these diagrams involve 2 anchor points and a scoot to the center. Also, if you do like that, you also get the same thing. I actually realised that there's a 5th. If your 2 points are so far apart that they're on opposite ends of a diameter, when you scoot to the center, it's basically just a straight line. Okay, so that's another diagram where 2 anchor points, scoot to the center, also scoot to the circumference. That's another look. Now this one is the weirdest look. If instead of scooting to the circumference, instead of scooting to the other side of the diagram, you instead imagined that your 2 points were super far apart. Now, me just turning the diagram around doesn't mean they're any further apart, but what I mean instead is, instead of imagining that these are quite near, imagine that they're really far apart because you have to go all the way around that way. That certainly makes them far apart. So in other words, when you scoot to the center, you scoot backwards. Now, the diagram for this diagram looks like this if you now scoot to the circumference. And so the angle when you scoot to the circumference, this is the theorem, is always twice when you, the angle when you scoot to the center is twice the angle when you scoot to the circumference. So if that's x, that's 2x. I'll do these other ones now. If that's w, that's 2w. If that's a, that's 2a. If that's b, that's 2b. And finally, well, we don't actually need letters for this. That is 180, and that's therefore 90. And this leads to another famous thing, which is that when you whenever you draw a triangle using a diameter, you always get a right angle. Okay. Just one other little fact about angles in circles. Comes from this quite special diagram. If you get a triangle that looks like it's been split in half, there are 3 questions you can ask about it. Is that the center? Is this a right angle? And is that the same as that? Now, you cannot answer yes to any 2 of those without also answering yes to the third. In other words, if I tell you that's the center and I tell you that that stretch is equal to that stretch, you can be sure that that's a right angle. If I tell you that that is equal to that and that's a right angle, you can assume without even being told that that is the center. If I tell you that's the center and I tell you that's a right angle, you can assume that that's equal to that. In other words, you cannot have 2 of those 3 things without also having the third. That is called perpendicular bisector through the center. And that's very useful. Now, for actual questions on these sorts of things, I recommend nice big diagrams, which is good because in the GCSE the diagrams are always big anyway. And you just literally go and try and find your shapes, colour them in when you're doing your study. You won't be able to do that in the GCSE, but just go and try and find the shapes. So that is me finding and labelling in pink a triangle that's built using a diameter. And this is me finding and labelling in green a rocket. Not a rocket, a butterfly. And this is me finding and drawing in purple a 4-sided figure, all 4 points of which are on the circumference. That's called a cyclic quadrilateral. That's for another video. This is just me illustrating just how much stuff you can find in any one diagram. So, which things are useful for us there? Well, I got this question out of a book. A whole bunch of angles, but always do dear Mr. Examiner on this. Just get yourself into the groove. Find things even though you're not asked. This pink triangle is built using the diameter, so that's definitely a right angle, which means that's got to be 61. So DEF, just don't write anything down yet, we're just getting in the groove. What else? Okay, that's got to be 12 because of the green butterfly, and that's enough to be getting on with. Now let's see what we're actually asked for. We're asked for EDF. EDF. Okay, well, that pink triangle is built using the diameter, so I could have drawn a pink triangle here as well. So that would be 90, so EDF equals 78. The official name for finding a right angle triangle using a diameter is angle in a semicircle. What else could I find? DEG I've been asked for. DEG, so that's DEG. Okay, well, my initial labelling wasn't very good because I drew this butterfly. I could have also done this butterfly. With that butterfly, that 29 also has to be that 29. So DEG equals 29. The official name for that is angles in same segment. Don't ever write butterfly, write the official name. And finally, you're asked for EGF. EGF. If that's 12 and that's 90, that's got to be 78. And you can also regard that, use that same butterfly that I didn't draw. If that's 78, that's got to be 78 as well. So you can say angles in same segment as well. Or you could say angle in a semicircle again.